Okay, so we looked at this earlier when we did some graphing on the calculator. And so we talked about the difference between a function whose domain is in the real numbers and produces a continuous and differentiable graph versus when our function has a domain in the natural numbers. So we have a disconnected graph. So we lose our continuity and therefore we lose our differentiability here. Okay, so that means that when we're finding the limit, if we need to use something like L'Hopital's rule depends on our function being both continuous and differentiable. So we're going to need to convert this over into x and use some of the techniques we learned in Calc 1 in order to figure out what's going on with our sequence, and then we can apply those results back to our sequence. We're going to do a similar thing when we study the integral test for series next week. So it'll be a similar tactic where we're converting into x and then using our calculus skills and then returning those results back to sequences. All right, so with that in mind, let's take a look at this theorem. So note that sequences in series are not continuous and differentiable. Therefore, we can't use L'Hopital's rule or find the antiderivative of series. Okay, so it does, however, turn out that if the limit of f of x as x goes to infinity exists, so if we're looking at the limit in the real numbers, and that limit exists and is finite, then the sequence a sub n equal to f of n will also converge to the same limit. So in other words, if I have the limit as n goes to infinity of a sub n, that is going to be equal to the limit as x goes to infinity of f of x. Okay, so if I need to apply L'Hopital's rule, I'm going to switch into f of x, which will give me the continuity and differentiability I need, and then I will be able to use L'Hopital's rule to find the limit. So let's start out with our sequence ln of n over n. So if we consider this limit here, so looking at the limit as n goes to infinity of ln of n over n, okay, this has the form of infinity over infinity, which is not defined. So I'm going to convert this to be the limit as x goes to infinity of ln of x over x. And I can apply L'Hopital's rule here. So I'm going to put an equals with an LH over the top to indicate I'm applying L'Hopital's. So that'll give me the limit as x goes to infinity. So the derivative of ln of x is 1 over x. And the derivative of x is just 1. Okay, so that really gives me the limit as x goes to infinity of 1 over x, which is going to 0. Okay, and so I know that the sequence of my sequence converges to 0, so I get that this guy converges. Okay, all right, so we're going to try this again with b sub n. And in fact, why don't you pause the video and give this a try all on your own. See how you do with that one. All right, so let's give that a try together. So we're going to start by doing the limit as n goes to infinity of n over e to the n. So again, that's that infinity over infinity. So I'll convert that into x. So I have the limit as x goes to infinity of n over e to the n. Both of those are continuous and differentiable, so I can apply L'Hopital's rule. And so I get the limit as n goes to infinity. So the derivative of n is 1, the derivative of e to the n is e to the n. So this is, again, basically like 1 divided by the federal debt. So this gives me 0, and I know my sequence converges. Okay, we have one more. Okay. So I'm looking at the limit as n goes to infinity of n plus ln of n over n squared. Okay, so that again is the infinity over infinity, so I can apply L'Hopital's, but first I have to switch it over to x. Okay, so if you don't switch this to x, then it is not correct because you can't take the derivative of a non-continuous function. Okay, so the limit as x goes to infinity of x plus ln of x over x squared. So I'll apply my L'Hopital's. Okay, so I have the limit as x goes to infinity. I have 1 plus 1 over x all over 2x. So I know as x gets really big, this 1 over x is going to go to 0, so that's going away. So what I really have is 1 over 2x. So again, this is 1 divided by the federal debt. This guy is 0. So I have that this sequence also converges.